So till now we could understand how the receptors or the transducers are stimulated and what happens thereafter. So the transduction wise, now we can understand the mechanical pressure or the thermal injury or thermal current or the thermal energy or the chemical energy. These have stimulated lots of receptors in the nerve endings, free nerve endings for pain, and now it will be propagated, and there are also at the same time both excitatory and inhibitory attempts to stimulate. There are also some inhibitory attempts also found in the peripheral nerves also, because due to the presence of opioid receptor, due to presence of endorphins, which are also liberated from the these Schwann cells or other tissues like the platelets or the epidermal cells. So they also try to reduce the sensitization. So there is a fluctuation, both facilitation and inhibition, even at the peripheral level, peripheral nerve endings. But finally, if the inflammation is more, if the insult or energy is more, then it will overcome the inhibitory effects and it will stimulate so that the inside of the nerve cells become more positive. Normally, if there is a nerve cell, there is an action, there are lots of fluids inside the nerve cells. There are also mitochondria, there are microtubules, and also the cytoplasm. And here, in the walls, there are lots of pores in the nerve cells. These pores are for the entry of different ions. Mostly the ions can enter in or go out. And inside this nerve cell membrane, if we put an electrode, we will be able to understand that inside the nerve cell, there is in the resting phase, there is minus 70 millivolt. This voltage is there, and it is stabilized in the rest. So more negative inside. Why? We know there are many ions, both cations and anions. They are both outside in the extracellular fluid and also in the intracellular fluid. To name the most important is sodium. The sodium ion, that is a positive ion. Inside the fluid, the sodium ion is about 50 milliequivalent per liter. But outside the cell wall, in the extracellular fluid, the sodium ion is 150 milliequivalent per liter. So there is a natural tendency of the sodium to go in due to its concentration gradient, and also there is another natural tendency of the sodium because it is positively charged and inside is negative. So the electrical gradient is also in favor of sodium influx. So sodium has a natural tremendous tendency to go inside the nerve cells, but it cannot, because these sodium channels, which these are blocked, normally it is blocked, and it can be initiated, it can be opened if inside becomes a little bit positive. Otherwise, at this negativity, the sodium gates do not open for the sodium, so sodium cannot enter in. And also the sodium, if inside the sodium also, they cannot go out easily. Now if the positivity is more, they have to be taken inside due to changing the electrical gradient of the sodium gate. Even while going out, they have to be moved with energy. They will be pushed with energy. Some amount of energy is necessary so that the sodium can go outside. Now coming to potassium. The potassium, it is inside the cell wall is a potassium bag. So 150 milliequivalent per liter is the potassium ion concentration inside, and outside it is only maybe 5.5 or similar or very near to that. coming. So potassium has also a tendency to go out, because the pores for the potassium, these pores for the potassium can go freely in or out. So potassium, nobody will inhibit potassium so that it cannot go out. So potassium gradient, concentration gradient is more inside, so it will try to go out. But at the same time, inside the cells, there are lots of these organic anions which are negatively charged. They actually catch hold of the potassium. They don't allow potassium to go out. That's why potassium is retained inside. So even for this negativity, and this potassium cannot go out, this more negatively charged, and it is minus 70 millivolt. There is another negatively charged ion, that is chloride. Chloride is negative, and this chloride also has a natural tendency to go out or outside. But inside the chloride ions, the concentration is very less. It is about 9 to 10 milliequivalent per liter. But outside it is more, it is about 125 milliequivalent per liter. So potassium can enter easily, but potassium will not be able to enter even if the concentration gradient is more, but the inside is electronegative due to anions. So this chloride will not be able to go in. So in this way, an equilibrium is reached when chloride will not go in or go out, when the membrane, inside the membrane, or the membrane equilibrium reaches at minus 90. This potassium, when it is minus 70, or sodium, when it reaches plus 60. So potassium, if the inside is more positive, it reaches plus 60, sodium naturally will not be able to enter in. Now, what happens in the actually, how the changes of the electropositivity and electronegativity occurs if we put an electrode inside the nerve cells. So electronegativity, it is fluctuating. It fluctuates, and it is called action potential. The membrane potential, which is minus 70, is sometimes it is positive, it is negative. So there is a rhythmic function. There is a definite logical movement of the ions which makes inside the nerve cells excited or more positive. So this is a membrane potential. Normal resting membrane potential is about minus 70 millivolt. It is resting. But when the inside the sodium starts going, how? At the resting membrane potential, there is a fluctuation. Both the inside the nerves also, sometimes it is becoming more negative, becoming more positive, so a little bit fluctuate. But somehow it stabilizes at minus 70. So now, if an insult and stimulus is given, maybe an electric current or maybe anything, so it is called stimulus artifact. And then, after a brief period of time, only it will start going up. So this is called refractory period. During that period, there is no movement. And then, as it starts moving up, after say 15 millivolt or so, when this inside membrane potential reaches minus 55 millivolt, then it is reached due to that stimulus. Now it is a time for the sodium. The sodium channels will open at minus 55 millivolt. So one door of the sodium is open and sodium will start going in. And once sodium starts going in, tremendously it goes in very fast. But keeping in mind that the sodium channels will not be opened for a long time, for a brief period of time. So it goes and very fast it goes up. So positivity of the inside membrane goes very fast. It crosses even the zero level and it reaches up to minus plus 40. It does not reach really to plus 60. It is supposed to reach because there are other factors too. One is the duration of the opening of the sodium channel is for a brief period, and another is that when it reaches 0 and then potassium channels are also open, that is potassium efflux. Actually potassium will go out so that it will not be that electropositive inside, and when it reaches about plus 40, potassium still goes out and the membrane potential drops again to negativity. So this part of the spike, this is called spike potential, is very sharp, and this part is called depolarization, and this part is called repolarization. So repolarization is due to potassium influx, depolarization is due to sodium influx, and then the potassium goes out, continues going out, and this is called after depolarization. This is after depolarization. And the final part, it goes out and it is after hyperpolarization till it stabilizes again at the membrane potential, resting membrane potential of the minus 70 milliequivalent. So this is called after hyperpolarization, and this is after depolarization. So this is a nutshell how the membrane potential of the inside the nerve membrane is kept fairly at minus 70 millivolt, and how it becomes positive. That means there is a propagation of electric current.